In the summer of 2021, a research vessel motored slowly along the edge of the continental shelf off the coast of Washington and Oregon, towing an array of seismic instruments designed to image the seafloor the way an ultrasound images a human body. The scientists aboard were not expecting to find anything dramatic. They were mapping familiar territory, a stretch of ocean floor that had already been studied for decades. Then the data started coming back strange. Somewhere beneath the waves, a slab of oceanic rock that should have descended smoothly into the earth appeared instead to be torn apart, one section dropping more than 3 miles lower than the rock beside it, as though something ancient had reached up from the depths and ripped the plate in two. Nobody on that ship fully understood what they were looking at yet. It would take years of analysis before scientists grasped what the tear actually meant, and by the time they did, it had raised more questions than it answered about one of the most feared geological structures in North America. This is the real story of the West Coast's most dangerous fault and why it is raising new concerns in 2026. Most Americans who have heard of this fault know it by a single, almost mythic phrase, the big one. But the geological reality behind that phrase is more precise and more unsettling than the shorthand suggests. The Cascadia Subduction Zone stretches roughly 700 miles along the Pacific coastline, from northern Vancouver Island in British Columbia down through Washington and Oregon to Cape Mendocino in northern California. Along this entire length, the Juan de Fuca Plate, a slab of dense oceanic crust, is being forced beneath the lighter North American continental plate at a rate of roughly 4 centimeters a year, according to data compiled by the Pacific Northwest Seismic Network. 4 centimeters sounds trivial, a distance you could cover with a fingertip. But multiplied across a fault system 700 miles long and accumulated over centuries of friction and locked pressure, that slow, invisible motion is capable of releasing some of the most powerful earthquakes ever recorded on the planet, in the range of magnitude 9 or higher, on par with the 2011 earthquake that devastated the Tohoku region of Japan and the 2004 Sumatra earthquake that triggered one of the deadliest tsunamis in modern history. What makes Cascadia especially unsettling to the scientists who study it is not just its size, but its silence. Unlike California's San Andreas Fault, which ruptures at the surface and produces frequent felt earthquakes that keep the public's attention fixed on seismic risk, Cascadia is almost entirely offshore and, by the standards of active subduction zones, eerily quiet. There has not been a great earthquake on this fault within the era of written American history. For decades, that silence led some residents of Seattle, Portland, and the small coastal towns scattered along the Oregon and Washington shoreline to assume the region had simply been spared, that whatever built the mountains and shaped the coastline had finished its violent work long ago. Geologists now know that assumption was catastrophically wrong, and the evidence that overturned it reads like a detective story assembled from 3 completely different sources on opposite sides of the Pacific Ocean. The first clue came from the trees. Along the Oregon and Washington coast, in places like the aptly named Nescoin Ghost Forest, the stumps of ancient Sitka spruce still stand in the sand, bleached gray, rooted in soil that is now regularly submerged by tidewater. These trees did not simply die of old age. Tree ring analysis showed that entire forests dropped suddenly, sinking several feet in what researchers call coseismic subsidence, the abrupt drop in land elevation that occurs when a locked fault finally slips and the overriding plate springs seaward, pulling the coastline down with it. The width and pattern of the outermost growth rings allowed scientists to narrow the date of this event to sometime around the year 1700, with the trees showing clear signs that they had died in winter based on the state of their outermost unfinished growth ring. The second clue came from 9,000 kilometers away, in the coastal archives of Japan. Japanese scholars had long preserved meticulous records of tsunamis striking their shores, and buried within centuries of documentation was an account of a tsunami that arrived on the night of January 27, 1700, with no local earthquake to explain it. Japanese seismologists and historians called it an orphan tsunami, a wave with no traceable parent earthquake anywhere nearby. When American and Canadian researchers cross-referenced the timing of Japan's orphan tsunami with the drowned forests of the Pacific Northwest, the 2 independent lines of evidence lined up almost perfectly. A massive earthquake along the Cascadia Subduction Zone on the night of January 26, 1700, had sent a tsunami racing across the entire Pacific Ocean, striking the coast of Japan roughly 10 hours later, a finding confirmed through collaborative research between USGS scientists and Japanese tsunami historians. The third clue came from the ocean floor itself, in the form of turbidites, distinct layers of sediment churned up and deposited by underwater landslides that only occur during major seismic shaking, layers that researchers have cored and dated at multiple points along the margin, building a longer record of Cascadia's past ruptures that stretches back thousands of years, revealing that great earthquakes here are not rare anomalies but a recurring, if infrequent, feature of the region's geological life. That turbidite record deserves a closer look because it is the primary tool tool scientists use to look past the single, well-documented 1700 event and into the deeper, pre-written history of the fault. When a great earthquake shakes the Cascadia margin, the violent motion dislodges sediment piled along the edge of the continental slope, sending it cascading downhill in an underwater avalanche that eventually settles into distinct datable layers on the abyssal plain far offshore. By coring these layers at dozens of sites along the margin and using radiocarbon dating on the organic material trapped within them, researchers have reconstructed a rupture history extending back roughly 10,000 years, identifying more than 40 candidate great earthquakes over that span, occurring on average every 200 to 300 years, though the actual spacing between events has varied considerably, with some gaps stretching for centuries and others compressed into a span of only decades. That variability matters enormously for how scientists communicate risk to the public. A recurrence interval measured in averages can create a false sense of a countdown clock, as though the fault owes a payment on a fixed schedule. The turbidite record instead suggests something closer to a loaded, irregular die, one where the last known great earthquake occurred 326 years ago, placing the region within the range of historically observed intervals between events, but without any physical mechanism capable of specifying which year, or even which decade, the next rupture will actually occur. For years, that combination of tree rings, Japanese tsunami records, and offshore sediment cores formed the backbone of scientific understanding about Cascadia, and hazard models built from that data-shaped building codes, tsunami evacuation routes, and disaster planning exercises across 3 states and a Canadian province. But science does not stand still, and 2026 has brought a wave of new findings that are forcing seismologists to reconsider several of the assumptions baked into those models, sometimes suggesting the danger is more complicated than previously understood, and in at least one significant case, suggesting it may be worse. The most consequential of these new findings emerged from a re-examination of the Juan de Fuca Plate's depth beneath the Oregon coastline. For decades, hazard models had relied on a particular estimate for how deep the subducting slab sits beneath key coastal communities. New research presented at the 2026 annual meeting of the Seismological Society of America revised that estimate substantially. Aaron Worth, a seismologist with the United States Geological Survey, reported that the slab interface near the coastline appears to sit at approximately 20 kilometers depth, roughly 5 kilometers shallower than earlier estimates had assumed. 5 kilometers might sound like a modest correction on a geological scale, the kind of number that belongs in a technical appendix rather than a headline. But in earthquake science, the distance between the rupture and the people standing above it is one of the single most important factors determining how violently the ground will shake. A shallower fault means seismic energy has less rock to pass through before it reaches the surface, less distance over which that energy can naturally dissipate. Combined with newly identified sedimentary basins, deep pockets of soft rock and loose sediment sitting beneath parts of the Oregon coast, including a previously underappreciated structure researchers now refer to as a hidden basin near Tillamook, the revised geometry suggests that some coastal communities could experience significantly more intense ground shaking during a future Cascadia rupture than earlier models predicted, because soft sedimentary basins are known to trap and amplify seismic waves rather than letting them pass through cleanly, a phenomenon well documented in other earthquake-prone regions, including the Los Angeles Basin. That same research season delivered a second, more ambiguous discovery, the one that sent that research vessel's strange data back through years of additional analysis. The tear identified in the Juan de Fuca Plate off the coast of Vancouver Island, first hinted at in data collected during the 2021 Cascadia seismic imaging experiment, was confirmed through more detailed seismic imaging published in early 2026. Part of the subducting plate in this northern segment appears to have fractured, with one section dropping several kilometers relative to its surroundings, evidence that the plate boundary here is not one smooth, continuous surface, but a fragmented, structurally complex system. When early reports of the tear circulated, some coverage suggested the northern portion of Cascadia might be, in effect, dying, gradually decoupling in a way that could reduce the earthquake hazard in that specific region. Scientists who study the fault directly have pushed back against that framing, cautioning that a tear does not equal a shutdown. Strain continues to accumulate in the segments that remain locked, and researchers studying the fracture note that increased structural complexity can just as easily complicate how ruptures propagate, potentially altering which segments break together during a future earthquake, rather than simply lowering the overall risk. In other words, the fault is not quietly retiring. It may simply be more geologically complicated than the relatively clean, uniform models scientists had relied on for the past several decades. This distinction between a fault segment weakening and a fault segment simply becoming harder to model is one that seismologists have had to explain repeatedly to a public eager for reassuring headlines. A subducting plate is not a single rigid sheet of glass that either holds together or shatters outright. It behaves more like a heavily creased and folded piece of material capable of tearing in one place while remaining fully locked and accumulating stress in another, immediately adjacent section. Researchers studying the Vancouver Island tear have emphasized that their findings say nothing definitive about the earthquake potential of the central and southern segments of Cascadia, which extend across the entire coastlines of Washington, Oregon, and Northern California, and which, according to existing hazard models, remain capable of producing the same magnitude 9 scenario long used in regional emergency planning, regardless of what is happening structurally hundreds of miles to the north. A third strand of research, published in February 2026 in the peer-reviewed journal Science Advances, added yet another layer of nuance. A team of researchers at the University of Washington completed the first long-term offshore strain monitoring study of the Cascadia margin, drawing on 13 years of ground motion data collected from seafloor sensors. Their findings challenged a long-standing assumption that the entire subduction zone behaves as a single, uniformly locked fault waiting to release all at once. Instead, the data showed meaningful regional variability. The northern portion of the margin does appear tightly locked and largely quiet, consistent with older models. But the central region, researchers found, behaves differently, showing evidence of slow, largely imperceptible fault slip and pulses of pressurized fluid moving through channels within the fault zone itself. According to the study's authors, that fluid may be relieving some of the stress that would otherwise accumulate in the central segment, potentially reducing, though not eliminating, the likelihood of a single margin-spanning rupture originating there. One of the researchers involved in the work explained that when fluid is not trapped within the fault, it may act as a kind of pressure valve, though the team was careful to note that the relationship between fluid flow and actual rupture dynamics remains an open question requiring further modeling. This finding does not mean Cascadia has become safer. It means the fault may not behave as a single monolithic hazard, but as a patchwork of segments with genuinely different behavior, a distinction that matters enormously for anyone trying to model how a future earthquake might unfold, how far it might extend, and how strong the resulting tsunami could be. Perhaps the most alarming development of the year, at least for public attention, involves not Cascadia alone, but its relationship to the fault system most Americans already fear, California's San Andreas. The connection traces back unexpectedly to a navigational error. In 1999, a research cruise setting out to study ancient Cascadia earthquakes drifted off its intended course, and in doing so collected seafloor sediment cores from an area scientists had not originally planned to sample. Buried within those cores, researchers eventually identified paired sediment layers, evidence suggesting that a major Cascadia earthquake and a major San Andreas earthquake had occurred in close succession, seemingly linked rather than coincidental. That accidental discovery sat in the scientific literature for years before newer research, published in 2026, expanded on the idea using additional sediment records and statistical modeling. The emerging picture suggests that these two fault systems, though geologically distinct and separated by hundreds of miles, may be capable of triggering one another, with a major rupture on one system increasing stress on the other, enough to provoke a second earthquake within minutes, hours, or at most a few years, rather than the centuries of separation scientists had generally assumed. If confirmed by further research, this synchronization hypothesis would mean that some of the worst-case planning scenarios used by California and Pacific Northwest emergency management agencies, built largely around the assumption that a Cascadia earthquake and a San Andreas earthquake are independent, low-probability events unlikely to occur together, may understate the risk of a scenario in which both regions face major damage within the same narrow window of time, stretching emergency resources across an area encompassing nearly the entire West Coast rather than a single state. The mechanism proposed to explain this potential synchronization draws on a concept seismologists call static stress transfer, the idea that a major rupture on one fault physically redistributes stress across the surrounding crust, sometimes easing pressure in one direction while measurably increasing it in another, in ways that can be calculated using models of crustal elasticity once the geometry and slip pattern of the triggering earthquake are known. This kind of triggering is not a novel or fringe idea in seismology. Smaller-scale examples of one earthquake measurably increasing the likelihood of another nearby, sometimes within hours, have been documented on fault systems in California, Turkey, and Japan. What is new and still being actively debated is whether the geometry and distance separating Cascadia and the San Andreas, roughly the length of the entire Oregon coastline apart at their closest approach in Northern California, is small enough for this kind of stress transfer to meaningfully operate between two systems typically studied in isolation from one another. Researchers involved in the 2026 sediment analysis have been careful to describe their findings as suggestive rather than conclusive, noting that paired sediment layers indicating close-in-time rupture could, in principle, also result from two independent earthquakes that simply happen to occur near enough to each other in time to leave overlapping geological signatures, a statistical possibility that additional sediment cores and refined dating techniques are currently being used to test. While national attention tends to focus on the subduction zone offshore, researchers studying the region immediately beneath Seattle have been raising a different, though related, concern throughout 2026. Dr. Stephen Angster, a research geologist with the United States Geological Survey's Earthquake Science Center, led a study published in the GSA Bulletin examining a network of smaller, shallow faults running directly beneath the city and its surrounding communities, distinct from the Cascadia megathrust offshore. According to the study, branching strands within the Seattle fault zone, running roughly from Bainbridge Island toward Bellevue, appear to rupture considerably more often than the Cascadia megathrust itself, with a recurrence interval of roughly every 350 years based on paleoseismic evidence. Angster has described his work as an effort to determine when and how often these local faults break, information that could help refine the window for the region's next likely rupture. The significance of this research lies partly in its geography. A Cascadia megathrust earthquake, while catastrophic, originates offshore, giving the shaking time to travel before reaching major population centers, and in some cases allowing early warning systems to issue an alert of several seconds to nearly a minute before the worst shaking arrives. A rupture on a shallow fault running directly beneath a city offers no such buffer. The source of the earthquake and the people standing above it would, in that scenario, occupy almost the same point on the map. Seattle is not unique in facing this layered hazard picture, a distant megathrust fault offshore combined with a network of shallower, closer faults beneath the city itself. Portland sits near its own mapped system of crustal faults, including structures capable of producing earthquakes in the magnitude 6 to 7 range independent of any Cascadia rupture, while the Tacoma Fault, running beneath the southern reaches of the Puget Sound region, has produced its own significant historical earthquakes documented in the geological record. What distinguishes the Angster study is the level of resolution it brought to a fault system many residents assumed had already been thoroughly mapped. Using high-resolution LiDAR, a laser-based surveying technique capable of digitally stripping away vegetation to reveal subtle contours in the underlying ground surface, along with targeted excavation trenches dug directly across suspected fault traces, the research team identified branching fault strands that previous, coarser mapping efforts had missed entirely, a reminder that even in one of the most heavily studied seismic regions in North America, the underlying hazard picture continues to sharpen as survey technology improves.